Okay, welcome back everyone. So today we're going to do a basic proof by induction involving a basic result from differential equations, namely the Lagrangian of Ttn equals n factorial over s to the n plus 1 for all integers greater than or equal to 0. Okay, so let's get started with our base case, as we always start. So for a base case, let's just write it out. Base case. We'll take n equals 0 because that's a basic base case. So when n equals 0, we're considering the Lagrangian of 1, and by definition, recall that the Lagrangian, well, I'll put this out to the side. The Lagrangian of some function f of t is equal to the improper integral from 0 to infinity of f of t e to the minus st dt. So let's use that here. So improper integral from 0 to infinity of e to the minus st dt. This is some basic integration. It's nothing but minus 1 over s e to the minus st evaluated from t equals 0 to t approaches, well, to t approaches infinity technically, right? Because we can't really set t equal to infinity. It's as t approaches infinity. So what is this? Well, consider what happens when t approaches infinity. Notice that this thing is just 1 over e to the st. As t approaches infinity, this clearly shoots out to 0. So when we approach infinity, this goes to 0. When we plug in infinity, well, this term goes to 1, and this term goes to 1. So we're just left with this term, but by the fundamental theorem of calculus, we're subtracting this term. So the sign changes to a positive. So then this is nothing but 1 over s, which is the same thing as, well, 0 factorial over s to the 0 plus 1. And that's exactly what we wanted. So this is a check. Because if we plug in 0 here, well, we have 0 factorial over s to the 0 plus 1, which is the same thing as this. So base case works. So now, induction hypothesis. Induction hypothesis. So we suppose so we have, well, I'll just write it like this. We have some, all integers work up to some value k. So in other words, we have that the Lagrangian of, let's see, we have t to the k is equal to the integral from 0 to infinity of, let's see, so we just have our function here is t to the k, so t to the k times e to the minus st dt. Let's not bother working that out right now. That'll just require tons of basically integration by parts repeated k times, and we can't really do that. So we're not doing that. So that's our induction hypothesis. And now we want to show that this implies that, well, this implies this is equal to this, which by the induction hypothesis, we assume that for some value k, this is going to be equal to k factorial over s to the k plus 1. Okay. So now we want to show that the Lagrangian of t to the k plus 1 is equal to, well, obviously k plus 1 factorial over s plus 2. So consider the Lagrangian of t to the k plus 1. And by definition, this is equal to the integral from 0 to infinity of t to the k plus 1 times e to the minus st dt. And let's use integration by parts here. So let's just use the standard method. No tricks here. Hopefully you can actually see this fairly well. Okay. Anyway, we're not going to use the DI method or tabular. So, well, let's consider this. So we have u equals our polynomial function, as usual, t dm plus 1, and that implies that, I'm going to take these markers down, du is equal to n plus 1 t to the n by power rule. By the way, dt, can't forget that. dv is equal to e to the minus st dt, thus v is equal to, well, minus 1 over s e to the minus st dt. I don't know why I added that dt, it's not there. Okay, so now by the integration, integration by parts, we have u times v evaluated from 0 to infinity. So let's see what that is. That's 1 over, well, minus 1 over s, and maybe I should write it as such. Well, yeah. U, so we have minus s t to the m plus 1 e to the minus st. Okay. And then we have minus, so also I have to add this evaluated from t equals 0 to t approaches infinity, minus the integral of v du. Well, we have a minus there, so the minuses cancel out, and we take out the constants n plus 1 and 1 over s, so we have plus, yeah, let's write it as such, n plus 1 over s times the integral from 0 to infinity of, well, t to the n e to the minus st dt. Okay, and hopefully you already noticed something here. This is exactly the integral that we got from the induction hypothesis, because we assume that this, by the induction hypothesis, we have the k value, basically, we have that this holds for all values until some k, and when basically that implies that this is the case. So we'll be able to plug this in here in a second, and that'll finish the proof. But let's not do that yet. Okay. Yes, let's continue. So we have the following. Oh, and by the way, I think I may have made a small mistake here. Equals, oh, I put n here. That's my mistake. This should be k. Yes, because we plugged in the function t to the k plus 1. So replace all of these n's here with k's. U equals t to the k. Sorry for that. K, 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 k. Yep. Okay, good. Okay, so now let's plug this in. Well, it's pretty easy to see that. Well, again, by the same logic from earlier, we have 1 over e to the st. It's pretty easy to see that this exponential function will clearly grow much faster than this polynomial function. Thus, this, whenever approaches infinity, this goes to 0. But you can prove that with repeated L'Hopital's rule, or maybe even induction, if you'd like. I'm not sure if that would work, but maybe it works. That could be an exercise to the viewer, right? So anyway, when this approaches infinity, we get 0. And notice that if we plug in t equals 0, we get 0 as well. So this term goes to 0. So now we're just left with this. Okay. And by definition, by the induction hypothesis, this is equal to k factorial over s to the k plus 1. So if we plug that in, we just get that this is equal to k plus 1 over s times k factorial over s to the k plus 1. Choosing basic algebra. This right here, numerator simplifies to k plus 1 factorial. The denominator clearly simplifies to s to the k plus 2, which is exactly what we wanted. So this would be k plus 1 factorial over, well, if you really want to be specific, we have s to the k plus 1, which is the same thing as s to the k plus 2. And that's exactly what we wanted, because we've come from this to this. So if we plug in k plus 1 into this, we get the exact same here. So that is the end of the proof. Let's shade in that nice black box. QED. I don't know, something like that. Happy face. Okay. That is the end of the video, and have a nice day. Hopefully you enjoyed that.